Hello, my name is Marija. I'm a junior research group leader at the Cluster of Excellence FINRO. I'll be presenting the work of my research group in active sensing with agricultural robots. First, why do we use robots in agriculture? Well, here are some examples of conventional methods used in agricultural studies: static sensors, manual sampling, and piloted aircraft. These approaches require large amounts of money and labor, especially for missions that need high speed, flexibility, and precision. Using robots instead can save us time, costs, and labor while delivering high-resolution data at much lower risk. To fully exploit the potential of these autonomous systems, we need new workflows suitable for these technologies. On a simple level, we can just replace the conventional machines with manually driven or pre-programmed robots. However, we want more autonomous, targeted behavior where the robots can decide by themselves which actions to take next without us telling them what to do. So to make this concrete, here's some examples of decision-making scenarios where the robots should be able to interpret the state of their environment and reason about the best possible choices to make. And this capabilities are the focus of our research group. Our goal is to develop algorithms that allow robots to act autonomously to perform different actions on the farm. The main challenges we address involve decision-making in large, uncertain environments and on resource-constrained platforms. And specifically in this presentation, we want to focus on the application of UAV-based active sensing. We consider a single UAV monitoring a field and deciding where to take the next measurements. So let's overview the structure of an autonomous system to see how this can be done. So we assume that the robot is equipped with a sensor, for example, a depth or multispectral camera from which measurements can be extracted. These measurements are used to construct a map of an environment of interest, in our case, a field. During a mission, the planner uses these maps built online to optimize trajectories based on a mission objective, for example, to collect data as quickly as possible in unknown environments. And this process is repeated online during the mission so that the robot can adapt its behavior based on new information. So now that we understand the system, let's look closely into the field mapping module first and some of the work we did here. So what are some of the specific challenges associated with mapping fields? Well, typically we have large areas we want to cover and cameras providing very high resolution images. There may also be certain properties of the field that we want to capture, for example, spatially correlated plant growth. Moreover, if we're processing the images, for example, detecting plants, we need a map that caters for the uncertainty of these detections. And the main challenge is how can we incorporate all these elements in a single probabilistic compact map representation that we can use for planning and updating online. To address these challenges, we developed an approach called adaptive resolution Gaussian process mapping. And we'll explain the approach with an example. So on the left, we can see a synthetic field ground truth environment, assumed flat, and the right is the output of our mapping approach. So our approach has two key attributes. First, the grid cells of the map are stored in a tree structure, allowing us to adapt the mapping resolution based on the image content. And this enables retaining details in areas of interest using higher map resolutions while compressing less relevant information at coarser resolutions to save memory. So in the example, the yellower areas are mapped at high resolutions and high detail, where the blue or less interesting areas are compressed. Second, we use Gaussian processes to encode spatial correlations within the map, which increases robustness against measurement noise. This also provides uncertainty information for probabilistic mapping and planning. During a mission, the map is updated in an incremental fashion to avoid heavy computational burdens. We tested our approach using temperature data from a field near Bonn. The bottom left plot shows the ground truth temperature distribution on the field, and on the right, we see the output of our mapping approach. As can be seen from the grid structure on the right, we use high resolutions to capture higher temperature value areas of interest. This ability to adapt the resolution enables time and memory efficient mapping, making it suitable for online planning applications. Now, moving on from mapping to planning, we'll discuss how we can use these maps to find optimal paths for the mission. The core challenge in planning is developing algorithms to predict the value of potential actions without the robot actually executing them yet. And to decide which action to take is best, we need to be able to evaluate many possibilities in a high-dimensional problem space, which can be very computationally expensive. Therefore, our goal is to develop efficient online planning algorithms for resource-constrained platforms. Recently, we tackled this problem using deep reinforcement learning. Our approach relies on a realistic simulation environment where we first simulate active sensing scenarios. Based on the outcomes seen from the simulator, we then train a neural network to predict the value of taking certain actions. By exploring the space of actions in an intelligent way, we iterate between these steps to learn the most informative paths for data gathering. We evaluated our approach in simulation by comparing against baseline methods. We can see our results show that our approach achieved the fastest reduction in map uncertainty over the mission time, with much lower time needed for replanning relative to state-of-the-art online planners. This is because we only need a forward pass through the already trained network to determine the next best action to take, as opposed to reasoning about a very complex problem space. Finally, as a qualitative result, the third plot shows an example trajectory planned using our approach. So to summarize, I presented our work on decision-making for agricultural robots. We started with an overview of the key elements of making an autonomous system, then zoomed in to discuss specific approaches for field mapping and informative planning we developed. For further details, please feel free to ask us questions at DigiCrop, have a look at our papers, and reach out to our group. Thank you for your attention.